Hello, good evening, all. We will just wait for 1 more minute and then we will start our session today. So let us start our today's session. I am Anu, pursuing PhD from University of Hyderabad. I'll start sharing my slides. If it is not visible, please let me know. So I hope slides are visible. Before going into the session, let us just rewind what we learned in our last class. Last two classes, we were learning bioinorganic chemistry, where we learned about hemoglobin, myoglobin, hemocyanin. In the last class, we learned about 20 different amino acids, including glycine, alanine, valine, leucine, etc. And we also learned about hemerythrin, which is used in oxygen transport and has two iron centers. And it exists in colorless form in deoxy state and red violet in oxy state. We also learned about chlorophyll, which has magnesium in 2 plus state as the central metal ion and has a chlorine ring system. And also plastocyanine and azurin, which are blue copper protein. Okay, now we have just rewinded what we learned. Now in this class, we will be learning like bioinorganic chemistry is almost, we have covered some basic topics. Now we will be learning about isomerism, term symbol, RS configuration, tolerance test, etc. in this class. Okay. So the question we are going to take, 1 minute. Okay. Okay, so in today's class, the first question we are going to discuss is from 2014 GATE Chemistry, question number 16. The complexes COH2O4 Cl2 NO2 and COH2O4 Cl NO2 Cl are linkage isomers, positional isomers, ionization isomers, and optical isomers. So we will learn everything about the isomerism and isomers, and then we will answer this particular question. Okay, so before going into isomerism, we have learned about nomenclature of coordination compounds. Okay, right. So we will just rewind that also a little bit so that it will be also helpful because questions can be asked directly from naming coordination compounds. So how we will name? We have two parts here, a cationic part and an anionic part. So if a complex is ionic, always the cation is named first, followed by the anion. And if a complex is non-ionic, then we will give a single word name, one word name. Okay. Now, first we have to find the coordination part, right? Name the coordination part. In naming the coordination parts, every time we will write the name of ligands and then the name of central metal atom or ion. And in naming the ligand, the ligands can be of three types: negative, positive, or neutral. And negative ligands, if a ligand is negative like Cl, we will add a suffix O, like it will become chloro. Okay. or for example, other examples are Cn minus, F minus, it all becomes fluoro, cyanido, etc. Okay. And if a ligand is neutral, like H2O, mostly we will give the name as such, but in some cases like H2O, ammonia, etc., we have special names like aqua, amine, for CO, carbonyl, NO, nitrosyl. Otherwise, the names are same. Ethane 1,2-diamine will be written same. And if it is positive ligand is present, the suffix IUM, EM is added. Like hydrazinium, H3O plus will be hydronium, etc. Okay, so like that we will name this coordination sphere. And also, if like two different ligands are there, which one we will put first? It is based upon the alphabetical order. H2O is aqua and Cl is chloro. So A comes before C. So first we will write aqua and followed by Cl. And the number is represented by di, tri, tetra. So tetra, aqua, dichloro, cobalt, and the oxidation state will be written in numericals 2, 3 inside the bracket and followed by the anionic part. So this I was just telling so that you guys will remind how the names coordination compounds are named. We have given a class earlier, but just it was a reminder. So now we know how to name a coordination compound particular. So for example, if NiCO4 means nickel tetracarbonate, like that. Okay, once we know that, next let us move on to the next basic of the coordination compound, which is isomers. So isomerism means if two if two compounds have same molecular formula but differ in at least one property, they are called as isomers, and that particular phenomenon is known as isomerism. And the isomerism can be classified into two categories, structural and stereoisomerism. Structural means obviously the compounds have same molecular formula but differ in the structural arrangement of atoms or groups around the central metal atom or ion, and these are called as structural isomers. So these structural isomers are of four types: ionization isomerism, hydrate isomerism, linkage isomerism, and coordination isomerism. And stereoisomerism, when there is a difference in spatial arrangement, and these are of two types, geometrical and optical. Let us learn about one by one separately. So first, structural isomerism. And among that, the first subdivision was ionization isomerism. So ionization isomerism means in this, compounds will have same molecular formula but will give different ions in solution. Okay, so if in order to know whether a compound is if two complex are ionization isomers, we should know what are the ions that will form in a solution. For example, these two, let us consider these two complexes. In both complexes, the both has one platinum, 4 ammonia, 2 chlorine, and 2 bromine atoms, right? So, but when we dissolve it in solution in water, what we will get in this case, we will get PtNH3 4Cl2 2 plus and 2 Br minus. And in this case, we will get PtNH3 2 times Br2 2 plus 2 Cl minus, right? So the ions that are obtained in the solutions are different. So in this case, these two complexes are called as ionization isomers. Okay. Now, the next one is hydrate isomerism. So in this case, if you consider a particular coordination compound, water can exist in two forms, either as a ligand or as water of hydration. Like ligand means it can be inside the coordination sphere or as molecules of hydration like outside the coordination sphere. To type this particular water can exist. So from the name itself, you can understand hydrate means it indicates water. So water can be either inside or outside. Based on that, we will get hydrate isomerism. An example is given here, CrCl3.6H2O. All these three complexes have same molecular formula, but the number of water molecule existing as water of hydrations are 0 in the first case, 1 in the second case, and 2 in the third case. So these are called as hydrate isomerism. Now, the next one is linkage isomerism. So this happens when there is a presence of ambidentate ligand. So when we have learned about naming of ligands, we learned what is an ambidentate ligand. When a monodentate ligand can is capable of attaching to the central ion with like oxygen as well as nitrogen in this case, like that. If more than one donor site, if it is capable at not at same time, but if it is capable of donating or interacting with the metal you through different donor atoms, then it is an ambidentate ligand. So example is NO2 minus. In this case, NO2 can get attached to the central atom by nitrogen or by oxygen. So if it is attached via nitrogen, it is called as Nitri2N, or if it is attached via oxygen, it is called as Nitri2O. So if we consider this particular example, CONH3 5 times NO2 Cl2. So everything looks same, molecular formula is same, but the only difference is in the mode of attachment. So if we are naming such a complex, we will get like first cationic part, right? And pentaamine, first based on alphabetical order. Pentaamine, nitrito-N, because it is attached through N. So nitrito-N, cobalt, and here the oxidation state of cobalt will be 3. So in bracket it is 3 chloride. Whereas in this case, everything will be same. Pentaamine, nitrito-O, cobalt, in bracket 3 chloride. Okay. So this is the difference. This is what is called as linkage isomerism. The next one is coordination isomerism. So this happens when we have both cationic and anionic part as complex ions. So from the examples it will be clear. We have cation part as well as anion part. Both are having both are complex ions. So and the ligands might have been distributed in different way in both the complexes, but the overall molecular formula remains the same. These are called as coordination isomerism. So in this both case, we have 2 platinum, we have 4 ammonia molecule, and 4 Cl, right? So both the molecular formula is same, but the here only 4 ammonia, all 4 ammonia is in first complex, whereas here 1 ammonia is in second complex. So these are called as coordination isomerism. And also there is a special type of coordination isomerism which is called as coordination position isomerism. So for example, there are bridging ligands. Okay. So for example, I am writing OH, just an example it is. We have here OH, here, or here also cobalt, right? And if I have NH3 twice Cl2, NH3 4 times. Okay, so here we have totally 6 ammonia, 2 chlorine and 2 OH. And we also have CO, OH, CO, OH. Here we have NH3 thrice Cl, and here we have NH3 thrice Cl. So total number of ammonia is 3. 2 chlorine is there. Sorry, total number of ammonium is 6. Here also 6. 2 chlorine atom, 2 chlorine atom, 2 OH, 2 OH, 2 cobalt, 2 cobalt. So molecular formula is same, but the arrangement, distribution, or the placement of ligands with the 2 cobalt atom is different. So this is called as coordination position isomerism, happens in bridged complexes. Okay, coordination isomerism happens when both of it are complex ions, and coordination position isomerism is a special case where we have bridged complexes. Okay, now we know about structural isomerism. The next is stereoisomerism. In stereoisomerism, we have 2 types: geometrical isomerism and optical isomerism. And in geometrical isomerism is also called as cis-trans isomerism. This we all know what is cis and what is trans. If 2 identical ligands are adjacent to each other, like in the first 2 are adjacent to each other, it is called as cis, and if 2 are opposite to each other, it is called as trans. This is in the case of like coordination number 4, but also can be in coordination number 6 also, like in octahedral complexes. Like for example, if we have a central metal atom, cobalt, we have A, and here B, B. So this is trans. Okay. opposite to each other. But if we have COAA, B, B, A, A, it is adjacent to each other, and in this case it will be cis isomer. Similarly, we will have two complex if we have like bidentate ligand. How we will find out? An example of bidentate ligand is ethylene diamine. I will just take represent with AA, CO. We have. So if we have like a bidentate ligand means it will attach through two sides of cobalt and AA, here BB. So this is trans. Okay, similarly, if we have, for example, CO, in this case, if we have En and En or AAs, whatever it is, B, that means two similar type of ligands are adjacent to each other. In that case, it will be cis. And this case, when it is opposite to each other, in that case, it will be trans. So similarly, we have like FAC and MER also. That will happen when we have like for example MA3B3. In that case, we will get FAC isomer and MER isomer. So how we can find out a FAC and MER? I will just modify this. In this case, if we have A and A here, consider this as a planar, and here above and below you can consider a pyramid, right? So if we join these three, this will be like a face of the pyramid. So if three ligands are arranged such that it forms a face, then in that case it is called as FAC, and in other case it is called as MER, like A and B, something like that. So it does not form a face. In that case, we can tell that it has a MER isomer. So this is about geometrical isomerism. Now coming to optical isomerism. In optical isomerism, it is based on how the isomers rotate the plane of plane polarized light. So some compounds will rotate the plane of plane polarized light to right side, and some will rotate to left. Whichever rotates plane of plane polarized light to the right is called as dextrorotatory, and whichever rotates plane polarized light to the left is called as levorotatory. And D and L isomers together are called as enantiomers of each other. And trans isomers will not show optical isomerism due to the presence of plane of symmetry. Like for enantiomers means they will be mirror images of each other, and they are non-superimposable. The definition of enantiomers are they will be non-superimposable and will be mirror images of each other. So if it has a plane of symmetry, then it will be superimposable. So any enantiomers should not have a plane of symmetry. In trans cases, we can see that it will have a plane of symmetry, and therefore it will not show optical isomerism. Okay. Now we can move on to solving the question. Okay, we know about structural isomerism, stereoisomerism, and all its subdivision. Now, the complex given in the question is COH2O4Cl2NO2 and COH2O4Cl NO2Cl. So, what will be the isomers? Anyone? So if we see that inside the molecular formula is same, right? Inside and outside, in this case NO2 is outside, and in this case NO2 is inside. That means when we dissolve it in the in water, it will give different ions. So what is such kind of isomers are called? Anyone?
Ionization isomers.
Yeah, ionization isomers, correct. So these are called as ionization isomers. Okay, so just see whether it is giving different ions. If NO2 is both NO2 are inside, then see whether it is linkage isomerism NO2 or NO it is represented. But in this case, it is very straightforward. You have to just see, it will give different ions and you will get the correct option. That is option C, ionization isomers. Okay. So these are about isomerism. If you have any doubt, you can ask. Or else we will move on to the next question. So this question was asked in 2012 GATE, question number 45. The ground states of high spin octahedral and tetrahedral CO2 complexes are respectively. So we have four options. Okay. So what are these A, T2 and all? These are called Mulliken symbols and comes from group theory. I think you have learned there. In group theory, it comes A means singly degenerate, E means doubly degenerate, T means triply degenerate, and G means gerade or ungerade, and it comes from if a center of symmetry is present or not. Like in octahedral, if you see in the question itself, octahedral and tetrahedral respectively, right? So octahedral, all octahedral term symbols have G and tetrahedral does not have G. It's because octahedral has a center of symmetry, so that's why it has G, and tetrahedral does not have a center of symmetry, so we will not have G. And 1 2 etc are based on whether there is perpendicular C2 present and all. So this comes from the group theory. But even if you don't know that group theory itself, we will get to know the answer. Like we will apply some simple tricks and you will come to know the answer. Okay, so we will start solving. So first of all, what we need to know is term and term symbol. Without knowing this also, you will be able to solve this question after the end of this explanation. But still we will know that how, what is term symbol, because question can be asked from here also. Just to I have seen questions where they have been asking term symbols both in GATE as well as NET. So if they ask question like that, it is very easy, and 4 mark question also they can ask. So you will get in NET I am talking about. So you can get easily such mark if you know what it is. Okay. So there is only one difference between term and term symbol, and it can be a major difference, because in some question they might simply ask to give term, and in option they will give the term symbol as well as the term. So you might give this one as correct option. So you should know that term means n plus 1 L, and one J also included. It is called as term symbol. So term symbol represents the electronic state, where 2s plus 1 spin multiplicity, s is total spin, or you can 2s plus 1 or n plus 1 are both equal. You can just like memorize this, no need of memorizing this one. N meaning the number of unpaired electrons present. So n plus 1 will give the superscript. L you can easily understand from here. So we know if it d orbital 2 1 0 minus 1 minus 2, if it is p orbital we will have 3, and we will denote plus 1 0 minus 1. So if one electron is present here, then the L will be 2. If one more is present, L will be 3, like that. So you already know the two terms, right? N in this case, number of unpaired electron is 2, so n plus 1 is 3, and L is 2 plus 1, L is also 3. So based on L, we can represent it by, if L is 0, we will represent S, and if L is 3, we will represent it by F, and so on. So L is called as total orbital angular momentum, and J is called as, this J term is called as spin orbital coupling. And how we will find out J? That is also very simple. J is L minus S, if when it is less than half filled, and L plus S when it is more than half filled. Okay, so these are how to find N plus L, L, J, that we can calculate very easily. Let us take an example of D1 electronic configuration. So D1 electronic configuration means, what is N here? N is number of unpaired electrons. So what is N here?
1.
1, correct. So the superscript will be n plus 1 that equal to 2. Okay. Now what is the value of L here? It will be 2. 2 corresponds to D. Okay. So L is D. That also we understood. Easy. Now what is the value of J? This is less than half filled. So the value will be L minus S. If it is more than half filled, it will be L plus S. Here total spin is 1 by 2. So L minus S will be 2 minus 1 by 2. Okay. So this has no relation with the like it has relation, but no need of knowing this also in order to solve this question. But still I am telling you because questions has been asked from this term symbol. You should just know this one, n plus 1 L J. How, what is n, what is L, what is J, how to calculate this. If a particular metal is given, like transition metal nickel is given, nickel 2 plus, so what is its configuration? You know it will be D8, right? So from D8 configuration you can find out the term symbol very easily, right? So for that, just for your knowledge, I have been telling this. Now the next important thing that we need to know is that how this will split. If 0 like S P D F G H I etc are called as spectroscopic term. So if they ask spectroscopic term, you have to just calculate the L and then you have to write SP, whatever is corresponding, you have to write that. That's all. Now S, you can link it with S orbital. It has one, right? One orbital. So it will be A. A means singly degenerate. T, 3 it has. So it will be T, triply degenerate. D, 5. So 3 plus 2. E is doubly degenerate and T is triply degenerate. So E plus T, like that. And in octahedral, both are same. Just the difference is in octahedral, G is there because of the presence of center of symmetry. And in tetrahedral, G is not there because there is no center of symmetry. And this is easy to learn. It might look complicated, it is easy. The concept comes from group theory. If you are learning group theory, there you might have learned how, but still we will learn easily we will learn that how we will memorize these things. It is very easy. So S means A, that we all know. 1 1 A, and G octahedral. So first you put 1 1 in S and P. So now you just imagine that in S and P 1 is used. So next you use 2, like that. You can just for memorizing I am telling this, okay? It's not actually like that. It is based on the symmetry elements, symmetric with respect to C2 and all. But just for memory, because that is for multiple choice question, that is the very much important thing. So T2G, F means, remember F orbital, 7. So how we will get 7? 1 plus 3 plus 3, 7. Like that. You can remember it like that. Okay. So now we know how this will split. The most important thing we should know in order to solve this particular question is Orgel diagram. From Orgel diagram, we can solve this particular question. Okay, so this also we can learn very easily. So if we have D, how it will split? We have 2 plus 3, 5. That means 1 T2G and 1 EG. It will split. So just remember, in octahedral field, normal in coordination compounds, we can relate it and learn it. It will be easy for you. Just look at this part. Okay. So how normally in octahedral field, how it will split? It will split like below it will be T2G and below it and above it will be EG. Just remember this much in this case. So this small, it is here T2G, it is Mulliken term symbol, but I am just correlating so that you guys will remember. Below it will be T2G, above it will be EG. So in octahedral we know below it is T2G, EG. Write just octahedral. D1 octahedral. The first configuration comes is D1. D1 octahedral. Write it here, this side. Okay. Now if this is T2G, this will be T2G, same line. If this is EG, this will be EG, same line. So if D1 octahedral comes here, the opposite, that is D1 tetrahedral will come this side. Okay, you can learn like that. D1 octahedral, D1 tetrahedral, this side. Now, how we will know next term? Only D1, D4, D6, D9 will have the spectroscopic term D, and D2, D3, D7, D8 will have spectroscopic term F. Even if you don't know that, just learn that D1 octahedral is this side. That much is clear, right? Now just add 5 to D1, D6, you will get D6. So D6 octahedral is here. So now you know that D1 octahedral as well as D6 octahedral is here, meaning the opposite D1 tetrahedral and D6 tetrahedral will be here. Tetrahedral, in tetrahedral case, it will be same, just you have to remove the G. It will be same. Okay. Now you know D1 and D6. Now you have to minus this from 10. Just totally 10 electrons are there. So minus this from 10. So D1 corresponding D9 you will get. D6 corresponding minus it from 10 you will get D4. So now 2 octahedral is there, 2 tetrahedral you will have. So now you have this side tetrahedral, this side it will be octahedral. So it is a trick that you can use if you like it. If you don't like it, just leave it, and however you find it easy for learning, you just go with that, and you should be finally able to solve the question. That is the only thing. This is how I learned. So that's why I just told you. If you like it, take it. Otherwise, leave it. Okay. Now in the case of F, the orgal diagram is like this. So in this case, how you will learn? You know D1 octahedral if it is here. Now the next one is D2 octahedral. So start with D2 octahedral. And now add 5. D7 octahedral. So D2, D7, if you know it is here octahedral, the corresponding tetrahedral will be of this side. And similarly, 2 is here, 10 minus 2, D8, 10 minus 7, D3. Corresponding tetrahedral is here. So the corresponding octahedral will be this side. And you should know T1, T2, A2. This is from P. Like P will be T1G. It is why it is here, because sometimes they will ask from transition and all, which transition is possible, how many transitions are there, some questions are there. Let us not get confused with that. Just remember T1G, T2G, A2G. If you remember this side, it will be easy. This side will be easy. You have to just draw a line A2G, T2G, T1G. It will be easy. So this is how we have to remember, so that if one question is given, like for example Fe2 plus or something, so if it has like for example if they have given D6 configuration and they asked in octahedral field, so directly if you know the orgal diagram, we know that D6 octahedral and the ground state symbol is T2G. So from directly we can find it out. And if they ask D6 tetrahedral, that means the ground state will be EG, like that. So if we know this particular orgal diagram and the configurations related, you will get to know the answer very quickly. Okay, so what about D5 and D10? We didn't tell about D5 and D10, right? It's because its spectroscopic term is S, so it will not split. So that you can do, write directly. No need of splitting, no need of knowing which is ground state, because only one state it has. So it is okay, there is no problem with D5 and D10. But in case of other electronic configuration, you need orgal diagram. Orgal diagram correlates between the energies and this electronic terms in transition metal complexes. Okay, now if we know the orgal diagram, we can directly know the answer of electronic configuration D7. So because CO2, it is given CO2. Right, the electronic configuration is D7. So D7, where it comes, D7 octahedral and tetrahedral they have asked. So in D7 octahedral and tetrahedral, which are the ground state? That means among the three state A2G, T2G and T1G, which will be the ground one in octahedral and tetrahedral? That is what they have asked. So which will be it? In octahedral, what will be the ground state?
T1G.
T1G, correct. And in tetrahedral?
A2G.
In tetrahedral, it will be A2, but G will not be there. In tetrahedral, you should not write G. It is same, but should not write G. Okay?
Yes, ma'am.
Okay, fine. So now we know the answer, but still we will like mm, uh, write the term also, so that you will be familiar with that also, right? So here we have D7 configuration. High spin it has been written, so we are writing high spin D7 configuration. That means CO2 term will be the number of unpaired electron. First we have to find, it will be 1 2 3, and therefore n plus 1 will be 4. The value of L is 3 that you can calculate, meaning F. N plus 1 L will be 4F, and therefore the corresponding orbital diagram is for F. Right, and D7 octahedral comes here, and the ground state will be T1G, and D7 tetrahedral comes this side, and the ground state will be A2. And since we in question it has been given the n plus 1 value also, n plus 1 value is 4. So 4T1G and 4A2. So the correct option is option B, 4T1G and 4A2. So if you know just the orbital diagram, you will be just remembering D1 octahedral. Just one thing you have to remember, from that you can get the whole orbital diagram, how where each electronic configuration is present, and then directly you can get the answer. So it will save you a lot of time. So for example, if you have given Fe2 plus D6, so in octahedral and tetrahedral field, if it has been given, so D6 meaning it will come here, the spectroscopic term will be D6 octahedral, T2G, and D6 tetrahedral will be E, like that. So it will be very easy if you know this particular orbital diagram. And I have not seen any question asking from GH and all. So doing orbital diagram of D and F itself, you will get enough marks. But you can, if I don't think questions will ask from GH, but I don't know, year by year it is getting more difficult. Level is getting more difficult. So you can just go now. You know the basics. It will be easy for you. Okay.
Ma'am,
Uh,
ma'am, I have a doubt. In
uh,
spectroscopic term F, you've shown one p orbital is there T1G.
yeah, yeah.
How does that term comes, ma'am?
Actually, this term is not related to F. This is related to P. We have S, P, D, F. No, this P is this one. P is represented by T1G. But the energy comes in between this, like
Is it an
T1G.
excited state, ma'am?
No, no, no. It's not an excited state. It is the state of P, but the energy level comes in between the energy levels of F, so that it is included in the orbital diagram. Actually speaking, if F only F we are considering, it has only T1G, T2G, and A2G. This just comes from the P because the energy level is like in one question I have seen how many transitions will happen, or from T2G, which transition is more possible, something like that. So T1G P also get included there. It comes from P spectroscopic term, but it also get included. So that's why it is included in this orbital diagram, which is not a part of F spectroscopic term. Is it clear?
Yes, yes, ma'am. But what will happen for the electronic configuration from F to P then?
F to P means I didn't
Like
get.
F term we are getting after calculating that L plus S, right? L plus S, L minus S.
That is J. L plus S and L minus is J. F term we are getting from just L. Like if 2, 1, this is L. If only one electron is present here and one electron is present here, we will have 3 and we will get F term.
Yes, ma'am. For P term, it will be only one.
It will be only 1. Like total will be only 1. Like for example, if we have a p orbital 1 0 minus 1, if one electron is present here, then we will have the total L is equal to 1. Then
So
spectroscopic.
for d d orbital elements, we can't say P there.
We can get, but it will come in low spin octahedral and tetrahedral, and that we can get only from what is this called? Tanisobo Sugano diagram, something is there. No, from that only. In high spin octahedral tetrahedral complexes, only this many possibilities are there. Whatever we discussed from D, then D1 to D10, only this many possibilities are there. We can either get D spectroscopic term, F or S. That's all in high spin case.
Yes, ma'am.
Okay.
Ma'am,
In
ma'am, ma'am, how many transitions are possible in D7 octahedral?
in D7 octahedral here, no, actually that answer will be 3. That's why we have included here 1, 2, and 3, like that. 3 transition. This question has been asked, I think, in CSIR net in some year. I don't remember how many transitions are possible like that in D7 octahedral itself, I think. So some configuration where F term was coming and 3 transitions are possible. Only for learning that only we are including T1GP actually. Otherwise, for F, we have only A2G, T2G, and T1G. For transition, when it comes, it will get transition to the T1G of p orbital. So this question has been come in CSIR net in I don't know which year, but it has been come. Okay.
Ma'am, is there selection rule for these transitions also?
Actually, some selection rule are there, but I don't remember exactly what are the selection rules. In this case, actually, it's like gerade to gerade only. It will transition. Obviously, this will be all gerade only. So something else are also there that I have to check which are the transition rules. But I think mostly all the transitions are possible, like A2 to T2, A2 to T1, and A2 to T1P. All are possible in this case. That's why the answer was 3 also. I just saw it sometime before. So in this case, it is 3. In other cases, I have to check what are the other rules for transition. But mostly, in this particular case, it is 3.
Okay, ma'am.
Okay. Now, actually, I wanted to tell you guys that today might be my last class because we have to take 12 class as a part of this PMRF, and might be my last class. If you want to know anything related to PhD or PMRF, because fellowship is important while doing PhD, you can ask to me. Because you all guys are going for PhD, that's why you are preparing for net, gate, and all. So if you have any doubts, you can just ask me today. Mostly, I will not be having any more class. Okay. So now we will learn question number 27 from 2015 gate chemistry paper. Okay. So we have to find out the absolute configuration at C2 and C3 carbon in the following compound. So if I tell correctly, the only portion I have learned from organic while giving my CSIR is this stereochemistry, aromaticity. I'm not good at organic at all, but without even attempting, we can qualify. Like I did only physical and inorganic, so this is very easy even for me who didn't do any other organic. So it will be easy for you, and you can score such marks. You can score marks very easily in such kind of case. So this absolute configuration can be determined by Kahn-Ingold prelog system. So what we have to do here is that if we have a carbon atom, there will be like 4 different groups attached to a carbon atom, then only it will be chiral, right? So we have to give priority on these 4 groups attached around the carbon atom based on the atomic number. For example, if one group is hydrogen, one group is carbon, one group is bromine, so the highest atomic number is for bromine. So we will give 1 to it. hydrogen obviously will be the last. So we will give 4 to it, and the others we will give 2 and 3 based on the atomic numbers. Now, this is the first thing we should know. Now, the second thing is that the fourth priority group, probably it might be hydrogen or something else like CH3 if other group are bigger group. So whichever is the least priority group, it should be pointing away from us. That is one important thing, otherwise you will get opposite configuration. So it should be in a direction that is pointing away from us. Now we have to draw an arrow starting from priority 1 through 2 to priority 3. And if the arrow goes clockwise, the absolute configuration is R. And if the arrow goes counterclockwise, the absolute configuration is S. R for rectus in Latin, which means right, and S for sinister. Okay. Now, this is an example. So, let us imagine that here the highest priority group is attached 1, 2, 3, 4. So, 4 is pointing away from us. We have to just draw a arrow. So, this arrow is in clockwise direction. So, it will be R configuration. Similarly, if we have such a configuration, we will start from 1, 2, 3, and this is in counterclockwise direction. So, it will be S configuration. So if now this is easy because in both the cases the fourth priority group was pointing away from us. If the fourth priority group is pointing towards us, so what we have to do? In that case, we can interchange the two atoms. So that fourth will become last. So in this case, I have interchanged 4 and 1. So 4 is now behind, 1 is front. And every time you have to do like even number of interchange, then only the configuration will remain same, otherwise it will change. So now one time we have interchanged, one more time we have to interchange, 2 and 3 we have to interchange, 3 2. Now fourth is pointing away, we have 1 2 3 4 and it is clockwise, so the configuration is R. Okay, so now we can solve the question. So while solving the question, let us take the second carbon atom. This is the second carbon atom. So among this, it is easy for hydrogen. Anyway, it will be 4. It is easy. So we gave 4. Now we have carbon here, bromine here. Bromine has highest atomic number. It will be 1. This two are easy. So we have given this two. Now we have to find out among the other two. Both are carbon. So now what we will do? We have to check which groups are attached to this carbon. So if we consider this carbon, it has one oxygen, and double bond to oxygen means we can consider it like it is attached to 2 oxygen. So totally it is attached to 3 oxygen. Whereas in this case, one carbon is attached to only 1 oxygen, 1 carbon and 1 hydrogen. So this is attached to the groups with higher atomic number. So it will get the second priority and this will get the third priority. So this is the priority. So now I have written in a simplified way 1, 4, 2, 3. So what is the next step? 4 is pointing towards us. So we have to interchange in a way that 4 will point away from us. So that I have interchanged between 1 and 4. So 4 come here, 1 came here. Now even number of interchanges are needed. So we have to interchange between 2 and 3. So now we got, just we have to draw from starting from 1, 2, 3. So it is clockwise direction and hence the configuration is R. Similarly, if we do this one, which one will be fourth one? H. This is very easy. First H. We will give 4. Okay. Now oxygen, carbon, carbon. So oxygen will get the first number. So oxygen is first. The second case is Mn. We have to decide between these both carbon. This carbon is attached to 3 hydrogen atom, whereas this carbon is attached to bromine, carbon, and again this carbon is attached to oxygen atom, and this is attached to hydrogen. So compared to this carbon which is only attached to 3 hydrogen atom, this carbon is attached to more carbon and bromine. So this will get second priority. So what will be its configuration?
R.
R, correct. So in this case, there is no need of interchanging also because H is pointing away. So we will get the configuration as such. So R. That means both the carbon atom are having R configuration, and therefore the correct option is option D, 2R and 3R. Okay. Any doubt is there?
Ma'am,
Huh?
what if second and third priority groups comes on dotted and dark lines?
What? Second and third priority?
Second
And
or third, if they comes on dotted or a dark line, then what will be that?
like this.
Hmm?
No need of getting confused at all. You can like interchange between anything with anything, just you have to interchange two times. So you can interchange like 4 with 3 or 1 with 3 or 1 with 2, anything you can interchange, but you have to make the fourth one to be in the second position. Like for example, we have to interchange, like I interchange between 4 and 2 for example, so that it will become 4 will become in the last position. 4 2 1 3. Now you can interchange any other two so that the configuration remains same. So no problem, you can interchange anything, just make the fourth one to last position, that's all.
Yes, ma'am.
Okay. Or in like we have this Fisher also, right? So if we have Fisher 1 2 3 4 and all, you can imagine Fisher like this side to be wedged, like pointing towards us, and this to be dash pointing away from us. So in this case, if fourth is in vertical position, there is no problem, you just have to draw, right? So if like we have this, and we have like this and like this, and fourth position is here, we have 3 2 1 and all, fourth position is here, means whatever configuration we are getting, the actual configuration will be opposite to that. Like for example, in this case we have 1 2 3 counterclockwise, we are getting S, but since 4 is in pointing towards us, the actual configuration will be opposite to that, R. So this is what in Fisher projection. So in Fisher projection also you can find out the absolute configuration, and in this case also you can find the absolute configuration. Okay. So now we can go next question, or do you have to like any other questions? Okay. Now we can go on to the next question. It was asked from in 2015, question number 30. Tolerance test is -4. So we can learn about tolerance test. So tolerance test is also called as silver mirror test. You might have, many of you might have done in your graduation chemistry class. I also have done in my graduation. So it's very beautiful test. We will get a silver mirror on the side of the test tube, looking very beautiful. So in this case, we have tolerance reagent as silver, NH3 twice OH, and oh, this came little. Okay, so it basically distinguish between aldehydes and ketones. What basically happens is that this tolerance reagent are not stable. So in that case, we will prepare tolerance reagent in the lab itself, freshly preparing. So how we can prepare this? Just we have to mix AgNO3 with NaOH. We will get Ag2O, NaNO3 and H2O. And this to Ag2O, we will add ammonia solution, and until this Ag2O is a brown precipitate, right? So we will add ammonia solution until this brown precipitate is completely dissolved, and so that we will get such a complex. And this complex AgNH32 plus, and this particular complex is basically the tolerance reagent. Okay, now what it will do in the presence of aldehyde? In the presence of aldehyde, this will undergo reduction, it will undergo oxidation. It is an oxidation reduction reaction, and this will undergo reduction to Ag plus to Ag0, whereas RCHO will undergo oxidation to RCOOH. So if CHO group is present, we can identify that since silver 0 will be formed and it will be deposited around the test tube. Ketone will not undergo oxidation and hence ketones will not be it will not give positive tolerance test. So this is what is basically tolerance test, and it is used for detection of aldehyde, alpha hydroxy ketone, terminal alkenes and reducing sugars. So only this many things we should know about tolerance test. Not much deeper questions will be asked. Mostly it will be asked among the following compounds, which all will give positive test, which all will give negative test. These are the questions that are generally seen, like from tolerance test, Benedict's test and all. So these are the type of question that has been asked generally. So now in option, we have 4 options: mannose and glucose, sucrose, maltose. Okay, so among which the first mannose and glucose are easy. That's why I have, if you know the structure, it is easy because mannose and glucose has an aldehyde group. So it will give positive test. So there will be no confusion. But when we go into maltose and sucrose, we might have some confusion because these are disaccharides. So disaccharides, we should know that even if we know the structure of maltose, we can't see any CHO group, right? So how we will know that whether it will give or not? So first of all, let us learn about maltose. Maltose is disaccharide of 2 glucose unit. So what will happen is that this is C1 of 1 glucose unit and this is C4 and of another glucose unit. C1 and C4 will link towards each other through a glycosidic linkage. The link is called as glycosidic linkage. But in this case, this particular glucose unit can go into the open chain form and aldehyde intermediate will be present. So since CHO group is present, we will get positive tolerance test. So this might feel like, oh, we should know that it will go in aldehyde intermediate and all. No need of knowing anything like that. We already saw that tolerance test will differentiate between reducing and non-reducing sugar. So what is a reducing sugar? Reducing sugar means any sugar that has a OH group in the anomeric carbon atom. Anomeric carbon atom meaning the carbon atom next to the oxygen. That is called as anomeric carbon atom. So whether OH group is present in there or not. So even in any cyclic carbohydrate, the carbon which was initially carbonyl carbon, or in simply you can just think like this: the anomeric carbon will be the carbon that is found next to the oxygen atom, not not like CH2OH. In the opposite direction you have to see. Okay, oxygen atom, next to oxygen atom you have to see the carbon next to the oxygen atom which does not have the end unit like CH2OH, CH2O, etc. Just you have to look at the carbon atom next to oxygen atom which does not have any CH2OH or CH2O kind of group, and you have to see whether OH is present or not. If OH is present, it is called as a reducing sugar, and reducing sugar gives positive tolerance test. So in this case, if you know the structure of maltose, you will know that this particular carbon atom next to oxygen has an OH group. So this will give positive tolerance test, whereas in case of sucrose, it is a disaccharide of glucose and fructose unit. It is a non-reducing sugar. So if we consider both, here one oxygen is there, next carbon atom does not have OH because that OH is involved in the glycosidic linkage. Similarly, this carbon atom, if we see, it does not have a OH. So this is a non-reducing sugar and will give negative tolerance test. So this is about tolerance test, and therefore the answer regarding the tolerance test, which one it will be negative, it will be sucrose. Okay. So tolerance test is negative for sucrose. This is regarding tolerance test, and that's all. We can discuss a little bit about, I will tell just about Benedict solution also, because since I saw one question in GATE regarding that. So Benedict solution basically have sodium carbonate, sodium citrate and CuSO4.5H2O. So in this case, there will be color change from clear blue to brick red. Okay, because Cu2 plus is present initially in CuSO4.5H2O, it will get reduced to Cu plus, and which will give brick color, brick red color, red precipitate. So in the case whether aldehydes, alpha hydroxy ketone, etc. will be present, where it will oxidize and Cu2 plus will reduce to Cu plus, and the color will change from blue to brick red, and we will get a positive test. It is called as positive test of Benedict solution. And if there is no color change, that means it is either a ketone or not an aldehyde, not a reducing sugar and all. Okay, fine. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay, then fine. So I hope then, I don't know whether we will say again or not. So uh, this might be my last class. So, okay. I wish you best luck or good luck. Huh?
Ma'am, can you tell something about PMRF? Like, I heard that we have to score about 8 CGPA in our MSc.
Yeah, in it's like two method we will have PMRF selection, either lateral entry or direct entry. In direct entry case from MSc you should have 8 CGPA, and you should have done your MSc from IITs and all. Some universities are there. From there you should have been you should have done your MSc, or else the second way to get PMRF is through lateral entry. So in that case you have to do coursework in your PhD. First year of PhD, you will be doing coursework. In that coursework, you should have CGPA greater than 8.5. So if you have that and you are doing from some institute like University of Hyderabad, Institute of Eminence, or some IITs and all, and if you have coursework more than 8.5 grade, through after 1 year of your PhD, that time your coursework will be completed and you will have your grade point with you. So after that, you can apply through lateral entry channel. So these two way you can apply for PMRF.
Ma'am, while joining in PhD, like if we have CSR and we enroll there with CSR, after getting PMRF, we can switch to that.
Yes, we can switch to that. I was receiving JRF scholarship, but once I got PMRF, I stopped it, and you have to return the money. But first year you can get from JRF extra money. If you have got anything, you can return that money, and then you can start receiving PMRF scholarship.
Ma'am, you also joined through lateral?
Yeah, I also joined through lateral.
And ma'am, is there any other things after getting PMRF we have to show them our research and all?
Yeah, you have to show your research. Like for PMRF, every year there will be a review. You have to give a presentation, like 5 to 8 minutes. They will ask questions. Some professors will come like online. It was online for us. Professors from BHU came and interviewed us. So it depends on which university you are doing, and your professors from other university will come and take an interview. And you should have progress, and after 2 years of getting, at least you should have manuscript ready or paper ready, something like that. And you should do TA work, in the internal and external. Internal means you can assist your professor in some taking class or some lab work and all. That should be 8 hours per week, and you have to do external teaching assistance. That's what I'm doing through this NPTEL, teaching you guys. So that should be like 48 hours per year, like that. So that is mandatory for getting continuation of PMRF.
Okay. And ma'am, is there any decided number of seats, particularly for one lab?
Yeah, it's not about lab or department. They will tell that, like for example, in University of Hyderabad, one time they can tell 4 PMRF fellows. We will give 4 students. These 4 students can be from same department. 4 students can be from different department. They can give to 4 students. It's not compulsory that they should give to 4 students. It is not like that. If like it's basically based on your research proposal. So if your research proposal is, if they feel like it's good enough, then they will consider your application, and then you can get, maybe same from same lab 2 people can also get. There is no issue like that. But it there will be limit for each semester for each university, like 4 this year, 5 this year, like that.
Ma'am, can you tell some topics which are more interested towards those things which grab attention for the
Actually, if you are applying through lateral entry and all, basically in I don't know about direct entry. In lateral entry, you will be enrolled already in a lab. No, so in that lab, whatever you are doing, you have to give, because based on that research proposal, you have to publish a paper, and then you have to move forward through PMRF. So it basically depends upon your supervisor, your lab, your topic. So if your topic is working in biology related something, then your research proposal should be that, so that you can work on it. So if your lab is working on theoretical and you give something related to experimental, then you can't work, no. So that thing and all you will get when you once enroll in a particular lab.
yes, ma'am.
Okay, so basically, energy and all this kind of things are on more focus now, application related part. So the lab you choose, and the field that there will be some field that you like, right? So in that field, some application related proposal, even your supervisor will obviously will help you regarding all those things, and you will have an idea once you join the lab. Only before that, uh, it's difficult, because the lab should have the facility to do your idea. So you can either choose the lab like that, or the lab which you are getting like related to that. Maybe the thought you have might be something more specific, maybe something related to that will be the lab will be working on. So it depends basically on your lab and the instruments available and all, because you should be able to carry out your work and finish it and give reviews to PMRF committee.
Ma'am, the funds which are being collected will be used in our research or will it be yours?
Funds, actually you will get 75,000 fellowship, that is yours. The contingency, 2 lakh you will get per annum, and that will be used for lab. You have to buy utensils, I mean glasswares or chemicals, or like if you want to go for attending a conference, that are all require money, no. So all those kinds of money will be like you will use from the contingency that has been allotted, 2 lakh per annum for that. The other 70 75 rupees, 75,000, depending upon which year PMRF you are, you will get, and that's for you.
Ma'am, how many papers we have to publish in PhD?
That also depends on lab. Like minimum 4 papers are told to be good, and but in some lab it will be difficult to get papers, like some people working in bio related thing, porphyrin rings and all, it is very difficult to get a paper there. So we cannot compare like that. In some paper some lab you will get paper easily, so we cannot compare, like it depends on lab, and it depends on supervisor, and it depends upon which area you are working. So which area do you like, Aarti?
Ma'am, I did my MSc in HU itself.
Okay, I
I'm
thought so.
telling you.
I have taken, I have come to your lab to class to take attendance. No,
Yes.
yeah, I thought so when I saw Aarti. I was
Yeah.
like, whether this is that Aarti or not.
Yeah.
Okay, so you want to join here itself?
Yeah, I'm planning to write entrance.
Okay, good. Which professor?
I am actually interested in application part of organic chemistry. So I got
Okay,
4 seats it seems in the 2 semesters.
okay, good.
I
All
managed
the
to
best.
yeah.
Yeah.
Thank you.
So, is there anything else?
Ma'am, can we get your mail?
Yeah, it's 1919. I will type in messages for this.
Thank you for your kind informations, ma'am.
Oh, yes, welcome. 19. I am writing my mail ID. Mm, okay. In messages, you can see my mail ID 19chph14 at uohyd.ac. Sorry, A is there, dot ac dot in. So you can mail me in that mail ID if anything is there.
Ma'am, please provide video links also.
Yeah, yeah. Actually, we are giving to like them, but they have told us to create a YouTube channel and then put video links in there. So once it is ready, I have not created YouTube channel. So once it is ready, just created, not put. I have just uploaded in Google Drive. So once it is created, we will let you know. Okay.
Okay, ma'am. Thank
Oh,
you.
yeah, welcome. All the best to all of you. Do well.
Thank you. Thank you so much, ma'am.
Welcome.
Thank you, ma'am.
Bye.